The next important application of the dot product is the idea of a projection. So here's the idea. I have some vector b which points in some direction that I'm interested in, and then I have another vector that I'm interested in, a. And ultimately my question is to write vector a in terms of vector b. So that is, I want to write vector a in terms of a vector that points exactly in the same direction as b plus a vector that's perpendicular to b. So this vector we're going to denote a parallel, and this vector is a perpendicular. So again, we want to write a as a sum of those two vectors, one parallel to b, one perpendicular to b. Okay, so in the next couple of pages I'm going to show you how to do this. I'm going to help you develop a formula to do this, to find vectors a parallel and a perpendicular. And I just want to point out to you that the formula that I'm going to show you is just a little bit different than the one in the book. You're welcome to use either the one that I show you here or the one in the book. But if you use the one in the book, it's very important that the vector that you start with is a unit vector. So if b that's given is not a unit vector, you need to first turn it into a unit vector if you're going to use the formula in the book. Okay, so here's what we're going to do. First, we're going to focus just on a perpendicular, or a parallel, excuse me. We're going to try to find a parallel. So here's the key thing to notice. A parallel should be some scalar multiple of b, because it points in the same direction as b. So if you remember back to when we first introduced this idea, the easiest way to figure out what this scalar lambda should be is to in fact think about b first and scale b by 1 over its magnitude. So this is where the unit vector comes in. So I think about a unit vector that points in the same direction as b, and then I scale it by the length of the vector that I want. Well, what length do I want? Well, I want a vector whose length is exactly the magnitude of a parallel. So what I put in here is the magnitude of a parallel, even though I don't know what that is yet. So let me rewrite that so it's just a little bit cleaner. So I've written down two things here. I've written down the definition of the dot product, the geometric definition, and I've noticed something that I simply get from trigonometry. The cosine of the angle between A and B is simply equal to the magnitude of a parallel divided by the magnitude of the vector A itself. That's simply from trigonometry. So at this point, all we're going to do is we're going to do a little bit of algebra. I'll tell you what it is first, and then I'll write it down. So I'm going to take this value cosine of theta, and I'm going to plug it in here, and I'm going to simplify. So here's the first step. I have the magnitude of A times the magnitude of B times cosine of theta, which I'm going to write as the magnitude of a parallel, divided by the magnitude of A. And notice that the two magnitudes of A cancel, and what we're left with is the magnitude of B times the magnitude of A parallel. Okay, so remember what we really wanted was the magnitude of A parallel. That's what I need to finish this formula. So I'm going to solve this for the magnitude of A parallel. So the magnitude of A parallel is equal to 1 over the magnitude of B times the scalar product A dot B. So I'm going to take this equation and I'm going to plug it in right there on the next page. Okay, so here it is, but it looks a little bit messy the way it is, so let's group things a little bit. This is 1 over the magnitude of B squared times A dot B, and notice all of that is a scalar, and then I take that scalar and I multiply it by the vector B. Well, I think we saw a little while ago that the magnitude of B squared is the same thing as B dot B. If we didn't see it, it's easy to show. You can ask me if you don't see why this is true. And so there's a nice way to write this. I can write this as the scalar whose numerator is A dot B and whose denominator is B dot B, B dotted with itself. Notice all of that's a scalar, and then I multiply it by the vector B. So, if we've done all this work and we've calculated A parallel, then it's an easy matter to find the other vector that we wanted, A perpendicular. Remember that A was supposed to be A parallel plus A perpendicular. Well, if we simply solve this for A perpendicular is the original vector that we were given minus the parallel projection, and that should be a simple calculation. Okay, finally let's look at one application of the dot product and the projection in particular. So imagine you have a block here and you pull it along the floor in the direction D with a vector force V. So maybe you're pulling on a rope and the block moves along the floor in this direction. So the work done by this force is defined to be the product of the component of the force parallel to the direction of movement. So work is only considered only considers the force that moves parallel to the direction of motion. And so work is defined to be the magnitude of F parallel times the distance that you move the object times the magnitude of the vector D. And so if you work out all the details, I'm going to leave them out here for now, you'll see that the work is the dot product of the force with which you pull times the distance vector, or dotted with the distance vector that represents the object of the motion.